Hi, this is Carter Stanfield, and I'd like to talk to you for a few minutes about the effects of inductive and capacitive reactance on AC circuits. Here's our basic circuit. It has three different loads: an inductive load, which is a shaded pole motor, a capacitive load, which is a capacitor, and a resistive load, which is a resistor. Power is supplied by the variable transformer shown in the upper right corner. The wire nuts shown in the bottom right corner feed both the circuit and the power factor meter, shown at the bottom of the screen in the middle. The three loads are wired in series. Current passes through the motor, through the capacitor, through the resistor, and then passes through the donut measuring the circuit current. This circuit with resistive, inductive, and capacitive loads is often referred to as an RLC circuit. R for resistive, L for inductive, and C for capacitive. However, I want to be able to easily add or remove the motor or capacitor in order to show the effects of inductance or capacitance. To do this, I'm going to add a switch in parallel with the motor and another switch in parallel with the capacitor. Let's see how this works. Here you see a switch wired in parallel with the motor. Normally, switches are wired in series with the load they control, not in parallel. That would not work in this case because opening a switch wired in a series circuit would shut off the entire circuit. The switch wired in parallel removes the motor from the circuit by shorting across it. Current will not flow through the motor with no voltage difference across the motor. When the switch is off, current flows through the motor normally. When the switch is on, current flows through the switch instead of the motor. Now let's add a switch in parallel with the capacitor. It will work the same way. When the switch is off, current will flow through the capacitor, and when the switch is on, the current will flow through the switch. I will use an oscilloscope to show the effects of inductive and capacitive reactance on AC circuits. An oscilloscope is a voltmeter that displays a graph of voltage over time. The y-axis represents voltage levels both above and below zero. The x-axis shows time. Showing on the screen now is an AC voltage sine wave. The graph shows that the voltage rises and falls over time. Here we see the oscilloscope. The yellow line represents the voltage going into the total circuit. The blue line is the voltage across the resistor. The voltage across the resistor should be in phase with the current because resistive loads are always in phase. In other words, the current and the voltage are in phase with each other. So let's turn the circuit on. So now we see on the yellow the voltage, and the blue represents the current. In reality, it's the voltage across the resistor, but again, current through the resistor will be in phase with the voltage. That also shows us the phase of the current. So you see with a resistive load, the voltage and the current are exactly in phase. Now I'm going to bring the motor into the circuit, so we'll have the motor in series with the resistor. And now you see the current for the circuit lags the voltage, meaning the yellow line representing the voltage peaks before the blue line, which represents the current. I'm going to take the motor back out of the circuit and put the capacitor in the circuit. Now you see with capacitor, the current peaks before the voltage. So with the motor, the current peaked after the voltage. With the capacitor, the current peaks before the voltage. And now if I bring the motor back into the circuit, you see with both the motor and the capacitor in the circuit, then again the current and the voltage peak together. So the capacitor, the capacitive reactance from the capacitor is offsetting the inductive reactance from the motor. Here's just the motor. And here's just the capacitor, and here's both the motor and the capacitor. There we go. So if we look at the power factor of just the heater, just the resistor, and we look at the power factor, we see it's 1. Now that means that the volts and the amps are working exactly together, and the watts and the VA or volt amps are the same thing, basically, because all we're doing is making heat. I bring my little shaded pole motor into the circuit. Now we can see our power factor has dropped some, so it's like around 0.73, 0.74. Now, of course, this is a combined circuit of the heater and the motor, but you can see the effects of the inductive load are to reduce the power factor, meaning that now our amps and our volts aren't exactly working together. And if I go with just the capacitor, so now my power factor is 0.29. But then if I have both the capacitor and the motor in the circuit with the heater, now my power factor is back up to 0.99, so that our capacitive reactance has pretty much exactly offset our inductive reactance. So I hope this gives you an idea of what a capacitor does in a motor circuit. It helps offset the inductive reactance, makes the motor more efficient, and makes the start winding a different phase, the current going through the start winding, a different phase than the current going through the run winding. The current going through run winding on a PSC motor is not corrected with a capacitor, so it stays behind like this, and then the current going through the capacitor is with the voltage, and so the current going through the start winding will be ahead of the current going through the run winding.